So I'm going to show you two basic examples of trig substitution in this video. So if you've been confused on trig substitution, I think this is a great way to start to help wrap your mind around it. So these are the two examples that I'm going to show you. So the thing about trig substitution is that it's a method that we use when we have exhausted all other options and we don't know what else to do. It doesn't always have to be that. It could just be something that like pops out to you. But in both of these, so you can't use like u substitution to necessarily do this. Now, this integral is kind of interesting because there's technically an integration formula for it. But I want to proceed as if you don't know that integration formula because we can also use trig substitution with this. All right, so the way that I think is the most efficient and easiest, I'm usually not a huge fan of memorization, but in this case I think it's worth it because in general, if your integral has one of these forms in it, these substitutions will be the most efficient. Now, there are other methods of how to do trig substitution that involve like just kind of coming up with the triangle first and all that. And that's okay, but like the thing about that is that you tend to get less efficient substitutions. And if you have no idea what I'm talking about, that's totally fine. I'm just mentioning this in case you've heard of other ways that you can approach this technique. I think that this is actually worth memorizing, and this will lead you to the most efficient solution. After you've practiced it enough times, you kind of get it in your system. All right, so that being said, so with this example here, so I've got this 25 plus x squared, and I can't like easily use like substitution with this. So I can see that I'm out of options. And so what I'm going to do is I'm going to set my x equal to, so this is 25 plus x squared. So if I just look at this chart, right, so x squared, or a squared plus x squared, so this is now 25 plus x squared. So my x is going to be just a tangent theta. So my a squared in this case is 25, therefore my a is 5. So this will be 5 tangent theta. Now from here, you're really just doing like normal things that you would do with substitution. So I'm going to go ahead and take the derivative. So this will be 5 secant squared theta d theta. And I like this chart just because it also has like a pretty good hint for us as to what we need to probably watch out for. So we will most likely use this identity. 1 plus tangent squared theta equals secant squared theta. So let's just explore this now. So I'm going to make these substitutions. So my dx now is going to be 5 secant squared theta d theta. And then the denominator here, so I have 25 plus 25 tangent squared theta, and I need to take the square root of all this. Okay, so now in the denominator here, I can factor out the 25 from the top. Let's see, oops. 5 secant squared theta d theta square root of 25, and then this becomes 1 plus tangent squared theta. And so then, let's see, that's equal. So then I can rewrite this as 5 secant squared theta d theta. And this really just becomes 25 secant squared theta. So now I'm left with 5 secant squared theta d theta. And this will just simplify to 5 secant theta d theta, 5 secant theta. So then we can see some obvious cancellations. So I'm actually just left with the integral secant theta d theta. Okay. So in case you forgot the integration formula or the antiderivative for secant theta, so I have here just a quick reference sheet that you can pause the video on. So these are things that, at least in my class, that were assumed to know. And so here's my antiderivative for secant x. Sometimes people forget about these. I think these are slightly trickier formulas. Okay, so let's clear a little space. And so in this case, oops, wrong color. All right, so this is going to equal the natural log of secant x plus tangent x. Oh, sorry, theta, not x. We're trying to get back to x. All right, so now I need to determine what are the values of secant theta and tangent theta. And so at this point, we need to go back to our original substitution. So I now need to use this here. So if x equals 5 tangent theta, that means that tangent theta equals x over 5. And so if you think about your good old SOHCAHTOA, so tangent is opposite over adjacent. So that's going to help me set up the reference triangles. So that's a terrible looking triangle. Let's set up this one. So here's my theta. So here's my opposite, here's my adjacent. So then this side, just by using the Pythagorean theorem, this will be x squared plus 25. Okay, so now to get these different values here, so secant theta, so just in case you're like getting a little tripped up by the trig, so you can always go back to the fact that this is 1 over cosine theta. Cosine theta, so again, you go through your SOHCAHTOA, so that would normally be, so maybe I'll just write it all out for you. So cosine is usually adjacent over hypotenuse. Therefore, secant theta will be hypotenuse over adjacent. Okay, so in this case then, this will be the square root, let's see, kind of running out of space here, but this will be x squared plus 25 over 5. And then tangent theta, so now that's going to be opposite over adjacent, so that's just going to be x over 5. Okay, and so now, all right, so the final answer then is going to look like this. So let's see, maybe I'll write it in the green color. The natural log of 1/5 square root of x squared plus 25 plus 1/5 x plus c. Now, I've noticed that some books and even integral calculators, they take the 1/5 out. They like factor it out effectively, and they just put it into the constant. So you might see some books that talk about having like this c prime, and then they will say that this is equivalent to the natural log of the square root of x squared plus 25 plus x, and then this plus c. So this means that this like 1/5 is kind of like grouped into this c right here. So they're literally the same thing, but I've just noticed that, and so that could be a little confusing, so I wanted to state that. Okay, so let's take a look at this other example, again using trig substitution. So I've got the square root of 16 minus x squared, and knowing that we want to use trig substitution, so this is the format that we're talking about. So in this case, my x is going to equal 4 sine theta, meaning that my dx will be 4 cosine theta d theta, and so then this will be 16 minus 16 sine squared theta, and then the dx is now replaced with 4 cosine theta d theta. So now, let's see, I can take this 16 and factor it out. And I probably should have factored out the 4 here, but oh well, do it in the next step. Okay, so I'm going to bring this first 4 out. So this square root now becomes 16 cosine squared theta. That's because with this type of substitution, you're going to want to use the fact that 1 minus sine squared theta is equal to cosine squared theta. And then I've still got cosine theta d theta. So I'll clear a little space. And so then this square root is going to become 4 cosine theta times cosine theta d theta. And so then I can bring the other 4 out. And so now I've just got to integrate cosine squared theta d theta. And to do that, the easiest trick to use here is, so this is my list of just helpful identities that tend to come up a lot with integrals, so you can always pause and write them down if you want. So this is going to be the very helpful identity in this case, so we're going to rewrite this as 1 plus cosine 2 theta. So 1 plus cosine 2 theta divided by 2. Okay, I'll clear some space again. And now I'm actually going to factor out this 1/2. So 16 divided by 2 is 8. So I'll just put that in front. And so here's what I have to integrate now. So this will be 8 times theta plus 1/2 sine 2 theta plus c. Now we need to get down with our triangle. So once again, I'm going to use my original substitution, and I want to view this as sine theta equals x over 4. So if you think about your SOHCAHTOA, so this is going to be opposite over hypotenuse. And okay, so this is my opposite, this is my hypotenuse, and then this will be 4 minus x squared on this side. So now I can figure the rest of this out. So theta, I have to get theta by itself. And so if I look at this relationship here, how would I get theta by itself? I would use arc sine, right, or inverse sine. So this will be 8 times inverse sine theta, or sorry, inverse sine x, really inverse sine x over 4, right? So this whole thing here, if I wanted to solve it, I would just take, I'll just outline it for you. So I would take inverse sine of each side, okay? And so I'm left with this right here. And then I've got plus 1/2, so sine of 2 theta, okay. So now I have to think about what am I going to do with the fact that this says sine of 2 theta. And so now I think back to some more of my trig identities. So let me clear just a little space. And I'm going to write out a little identity that is going to be helpful here. So sine of 2 theta, I can use a double angle identity, which says that sine of 2 theta is 2 sine theta cosine theta. So it's completely possible and fair game for you to have to occasionally lean on your list of trig identities to figure some of these problems out. So this is just a simple Google search of like, what are all the identities, and then looking for, oh, I see a sine 2 theta. So I just did like a quick Google search and found something that looked exactly like this and gave me this output. So don't stress too much if you're like, oh, I'm not sure where to go. Like, you know, there's a lot of identities out there, so you might have to refamiliarize yourself with some of them. Okay, so this is now going to turn into times 2, let's see, sine theta cosine theta, okay? And so now, let's see, let me clear a little space again. Okay, so now sine of theta, let's see, I'll write this out one more time. Inverse, okay, so sine of theta, so that's going to be my opposite over my hypotenuse, so that's going to be x over 4. And then cosine of theta, so that's going to be the adjacent side over the hypotenuse, and then all of that plus c. Okay, and so now I can finally rewrite this. So this will be 8 inverse sine x over 4 plus this will be 8 over 16. So I'll just go ahead and write this as 1/2. 1/2 x times 4 minus x squared plus c. And so that will be the final answer in that case. So even though this is like one of your basic trig substitutions, like I think this is a good one to demonstrate, like sometimes as you're trying to figure out the answers, like sometimes these can get a little hairy even though the like start of it is like a more basic problem. And basic at this point is like, it's basic, but there's like nothing basic about it, right? So it's a little, like it's like the most straightforward of like which path, I guess, to start with it when we say basic. Okay, so that brings us to the end of this video. So if that was helpful, please consider hitting the like button. I'll catch you guys next time.